Okay, you should have out your lecture notes for lecture 20, more on random variables. All right, and this is just going to clean up a few ideas that I've kind of hinted at in previous lectures, but I just want to make sure we have them all kind of solidly together here. So our context is we have some random variable x that's the result of some random experiment, and there's an underlying sample space of outcomes, and the random variable is determined by whichever outcome, the value of the random variable is determined by whichever outcome happens. All right, and I point out here, you see that for a given value of the random variable x, the probability that capital X will equal that particular value, little x, which you write as probability capital X equal x, it's just the probability of the event E that's associated with that value of the random variable, the event E that contains all the outcomes that give us that particular value. So when we compute probabilities for random variables, we're computing just like we would be computing, we are computing probabilities for events, so we should expect that the number is always between 0 and 1, right? We should always have that 0 is less than or equal to probability x equal x, which is less than or equal to 1. So when we make a probability distribution chart for like a discrete random variable, we have the values on one side. All those probabilities on the next column for the probabilities, they should all be numbers between 0 and 1, just like when we compute probabilities for events, because that's actually what we are computing. All right. I want to point out here that a random variable, what it does is we say it partitions the sample space S. And so what that means is, first, it means that events associated with different values of the random variable do not overlap, right? If I have one value of the random variable, that corresponds to one event, a set of outcomes. If I have a different value of the random variable, that corresponds to a different set of outcomes. Those sets are different and they don't overlap. We say that their intersection is empty, is another way to say that. All right, so the events for different values of random variables are completely separate from each other, and all the possible values of the random variable taken together give events that cover the whole sample space. So we account for all possibilities when we look at all the different possible values of the random variable. So what that means is if you add up the probabilities for all the values of the random variable, it should always come out to be 1. I'm thinking right now of discrete random variables, which is the only kind of random variable we studied, and we'll talk about continuous random variables in a little while, but this should, next lecture maybe, but this should make a sense to you that each value represents an event, and when we add up or look at the probabilities for all those values, we're combining the probabilities of all those separate events, and it should total out to be the probability for the whole sample space, which is always 100%, or just 1. Okay, so in fact, let's look at that in the context of the experiment where we toss 2 fair dice, and the sample space is that set of 36 possible outcomes, right? And our random variable x we had was just the sum of the values on the dice. And I guess what I want to show is that, if I can do that here, let's look at the different events that correspond to different values of the random variable. Okay, so the lowest value of the random variable was 2, and that corresponded to the event, if I can get it up here, just 1, 1, right? The value 3 for the random variable corresponds to the event 1, 2, and 2, 1, right? Because those values, 1 plus 2 is 3 and 2 plus 1 is 3. The value of 3 corresponds to this event, and this is something you all, the value 4, corresponds to 1 plus 3, 2 plus 2, or 3 plus 1, right? Et cetera, et cetera, et cetera. I can keep going like this, and you should have done this back when you computed the probabilities for the random variable in a previous lecture. You should have done pretty much what I'm doing right now. And notice what I am doing, though. I am generating what would be called a partition of the sample space. Each value of the random variable gives me a completely different subset. There's no overlap. right? There's no overlap, and if I take all of them together, they get the entire sample space, don't they? And this right here is the event that x is equal to 11, and here's the event x is equal to 12. Isn't it true that if you look at those, all those sets are separate from each other? I'm never counting an outcome in an event for this one is the random variable is equal to 9, right? 3, 6, 4, 5, 5, 4, and it has nothing in common with this one over here, which is the event for the random variable having value 8. All right, they're completely separate. Furthermore, it takes care of all values. So down below, I think I say we note, all right, so what I would say is that we note that the events are disjoint. The events for different x values don't overlap, and together the events for all x values cover the sample space. They get every outcome, I'm just going to say cover S, they get every outcome in the sample space. Okay, there's, I guess, one other thing I'd like to stress, and that is that, see, I think I have it on the slide. Boom. Oops, it's overlapping a little bit. So I have this written, I'm going to rub it out. And you can read what that says there. This is just an aside that, you know, is probably worth understanding, and that is that there can be many events that don't correspond to any value of the random variable, right? An event is just a subset of the sample space, and I can certainly grab another event here. How about, let's say the event, I want the event where I think it was the second die is always 1. All right, the second die is always 1. That means 1, 1 works, 2, 1 works, 3, 1 works, etc. I actually get this event, don't I? I get this event right here. Okay, that event has nothing to do with the value of the random variable. It cuts across, you know, a lot of the values of the random variable, not quite all of them, but it cuts across events that correspond to different values of the random variable. And it's no big deal because I'm not really interested in that kind of an event. When I have my random variable, I've broken the sample space up into a particular set of events that are separate from each other and cover the whole sample space, right? But that doesn't mean I've got every event I can think of. I most of the time wouldn't have every event that I can think of. All right, let's see. I guess I do have one other thing I want to say, and I probably need to rub this out before I say it. Let's see, got a pretty design. Let's see, have I rubbed out enough to put the first line in? Yes, it's good to think probability equals area when we start drawing all these graphs, which we're going to be drawing, we've been drawing these histograms, and we're going to do other kinds of graphs soon enough. But especially with these discrete random variables, these probability histograms, it's not exactly always true that probability equals area. And the example I want to look at is, I want to go back to the 2 dice experiment and consider the random variable x bar, which it looks like I did not define. I did not define here. I thought I had it defined. So how would you define x bar? Let's see, I need the same color here. X bar is, where am I? Right. Equals, instead of just the sum, we'll make it be the mean. When you see a bar, that generally means the mean. Okay, so I want to look at Not just adding them up, but then adding them up and dividing by the number there are, dividing by 2. So I have actually what we would think of as the 2-sample mean random variable. And the question I have is, what is the probability distribution chart and histogram? Very, very similar to for the sum. And so pause me, please, and figure that out. Drawing the distribution chart and the histogram. They're going to look very similar to what we had before, but we have to change a few numbers on it. So please pause me while I rub this out and draw that in, the chart and the histogram. And then I will put them up. Okay, the big difference is that, of course, when I divide by 2, I'm not going to get values between 2 and 12. I'm going to go back to getting values between 1 and 6, right? But now they go up by halves, right? Because whereas I had 2 before, when I divide by 2, I get 1. Whereas I had 3 before, when I divide by 2, I get 3 halves, etc., etc., etc. All right, I'm stopping it here because I want to make sure you understand this. This is a point of confusion, excuse me, for some of you students. And the diagram, if you've drawn the chart and the histogram, many of you probably have it labeled incorrectly. So I want to make sure we get this right. So look at the values now. They are 1 through 6 instead of 2 through 12. And that's because we're dividing the sum by 2. And how do we get these probabilities over here? Well, let me jump all the way back, if you will, to about, sorry, too far, about right here. Let me back away. Yeah. Okay, look, excuse me. This first one right here corresponds to the sum being 2, correct? That also corresponds to the mean being 1 because it's 2 divided by 2. Okay, so in that chart we'll go back to in a minute, but the value for 1 should be, well, there's only 1 out of all 36 here, so the probability should be 1/36. What's the very next value? For the sum, it's 3, and that's this event right here, which of course corresponds to later on when we're doing the mean, it's 3 halves because it's 3 divided by 2, right? So 3 halves should have the probability 2/36. Let's jump to another one right here. Let's jump clear over to this one. This one corresponds to the mean being 4, doesn't it? Because if you add these up, they each add up to 8, so it's the event the sum is 8, which is the same as the event that the mean equals 4 divided by 2. And what do we have? 1, 2, 3, 4, 5. So we should see that the mean being 4 has probability 5/36. Okay, let me shoot back ahead to where we were and kind of let me go back and go forward again. I'll stop it again here in a minute because I have something else I want to say, but I want to make sure you understand this and get your both your chart here correct and the labels on your histogram correct, because I've noticed in the past students have had trouble with this. So here we go. Whereas I had 2 before, when I divide by 2 I get 1, whereas I had 3 before, when I divide by 2 I get 3 halves, etc., etc., etc. So those are the possible values. The same probabilities are sitting over here, right? There you go. For 4, oops, I don't want to move the thing. For 4, I have a probability of 5/36, like we saw, right? So it should make sense to you. Jump back to, it was, the time was 5:42, or around there, if you want to go back and look at that previous chart. But it's very similar, just the numbers, the values are divided by 2. Probabilities stay the same. Oh, that's all the same. And what it does is it changes then. I didn't fill in this, the histogram. You should fill it in if you haven't, but so right. Okay, the midpoints were, before for the sum, they were 2, 3, 4, 5, all the way up to 12. But now it's the sum divided by 2. It's the mean. So along the horizontal axis, here's what the labels should be for the midpoints of the histogram. Here I have 1, and over here I have 1.5, right? 3 halves. And over here I have 2, and I'm just going to say, etc. I'm not going to do the rest of them. And of course, right up here I have probability 1/6. No, that should be 1/36
For x equal 1, the probability is 1/36. I just wrote 1/6, my mistake. The next one I'll write should be 2/36, and I think I say 2/6 too. That's just a mistake. Sorry. Those should be 1/36, 2/36, etc.
And then up here I have 2/6. Again, I'm not going to fill those in. You should fill all those in. But I guess I just want to point out one thing, and that is that look at the first bar. It corresponds to probability 1/6, but really,
No, it corresponds to probability 1/36. But you got that now. All right.
what are the left and right endpoints of the bar? They're actually, it goes from 3/4 to 5/4, right? To be in between, this one here has to be in between 1 and 3/2. So it goes to 5/4 and down to 3/4. That's a width of a half. This has a width of a half, etc. And of course, that's because we're going up by halves over here. So really, the areas are not right because the height is 1/6. That corresponds to the probability. I'm not going to multiply by 1. I'm going to
1/36 is the height. All right.
multiply by half. So if I were getting area, so the area is not giving me the correct probability. So I just wanted to point that out, that I kind of maybe hinted, led you to think that the areas of the bars in the histogram are always going to give you the right probabilities. They don't. You look at the heights of the bars, the areas will give you the right probabilities if those widths are always 1, okay?
It is true that we could just alter the heights so that the area always gave us the correct probability. We could do that. We could just adjust the heights so that the area gave us the correct probability. I think typically when you see a histogram, you don't have that. You have the heights giving you the probability. So as long as these widths are not 1, that means the area of the bars is not the correct probability, just the heights.
Nonetheless, it's going to be very advantageous for it to think in terms of probability being area when we get to talking about continuous random variables, and that's where we're going, if not the next lecture, probably the one after that. And there we'll see that area really is crucial to think of probability in terms of area. All right, I guess I will stop there. I can find my button. Here it is.
All right, we will stop here.